Today we're starting 7.4. It's all about inverse functions. There's a lot to learn about inverse functions, so our notes today are going to be a little longer than usual, not super long. And then tomorrow you will have class time to work on the homework for this section. All right, here's the definition of inverse functions. I typed this straight out of the book. So if you don't feel like writing a bunch today, this is available in your book. But this says, an inverse relation maps the output values back to their original input values. This means that the domain of the inverse, that should say is, the range of the original relation, and that the range of the original relation is the domain of the domain of the inverse relation is the range of the original relation. It's a mouthful, right? Basically what we're learning today is something called an inverse. If it's a function, we call it an inverse function. If it's just a relation, we call it an inverse relation. Essentially what you do when you're finding the inverse of a function, you take the x values and you change them to the y values. And you take the original y values and you change them to the x values. We call this an inverse function or an inverse relation, depending on which one it ends up being. Now, the way we say inverse or the way we write it, this is the inverse function of f, or f inverse. It's with the, it kind of looks like an exponent. It's not really an exponent. Of a negative one between the f and the x. So anytime you see that, we want the inverse. And remember, the inverse, you just take the original x's, make them the y's, the original y's, and make them the x's. This is an extremely important idea when it comes to inverse functions. So the graph of an inverse relation or an inverse function is the reflection of the graph of the original relation over the line y equals x. So y equals x, we know just from slope-intercept stuff that it starts at 0, right, and the slope is 1. So it goes through 1, 1, 2, 2, 3, 3, 4, 4, and the same thing in the negative. If this is your original function, the blue parabola you see, you would reflect it across this line, and that would give you the inverse. Now, you couldn't call this one an inverse function because this one doesn't pass the vertical line test. So this would be just an inverse relation. Okay, so if you're graphing the inverse, one should be a reflection of the other across this line. Okay, so here's a parabola, and here's what it looks like when it's just linear. And remember, reflection is kind of like taking your graph and folding it across that diagonal line, and they should line up with one another, the inverse and the original. Any questions on this idea? In this one, the originals are in blue and the inverses are in red. The green line is the y equals x line. Today in your homework, it's going to be divided up in a few different sections. One of the sections looks like this. It says that you need to find the equation for the inverse relation. So when you're finding the equation for the inverse, these are the steps you're going to follow. You're going to write out the original equation or the original relation. You're going to switch all the x's to y's and all the y's to x's. Then you solve for y. And then here's a little special note for you. Some of them are written in function notation, so it'll say f of x equals some x expression. Some of them will say y equals some x expression. You should know that those are the exact same thing. So if it's written f of x, now you're changing all the x's to f of x and all the f of x's to x's. So just be aware of that. They're interchangeable. And then just notation-wise, remember if you're using function notation for the inverse, you should have the little negative one in between the f and the x. All right, here's the first one. So you want to start by just writing the original equation. It's a pretty easy one. Y equals 4x plus 8. Now, here's the magical step. Ready? You are changing the place of x and y. So your y becomes an x, your x becomes a y. But we want to write it in that original form. For a linear equation, we want to write it in slope-intercept form. So I need to solve for the new y. So I'm going to subtract 8 from both sides. Then I'm going to divide both sides by 4. So I end up with y equals 1/4 x minus 2. We're following the exact same steps on this one. So you start by writing your original function. Then to find the inverse. You are going to change every y to an x and every x to a y. Here is the magical step. Oh. Can I leave it like this? Yeah, you can't leave it like this, okay? But this stuff isn't hard. You guys have been doing this for years. You're just getting it into slope-intercept form. Yep, -3. Good, so we have -1/3 x plus 4. Alright, so here's number 3. Again, we're just going to write the original. Do the little swap. Change your x's to y's, y's to x's. This one's just a tad harder to get the y by itself because of that fraction, but it's definitely manageable. Yeah, we're going to multiply both sides. You can do it in 2 steps by 3 and then divide by 2, or you can just multiply by the reciprocal. You guys know that. That's Algebra 1 stuff. To undo fraction multiplication, you multiply by the reciprocal. I think I'm missing a parentheses, aren't I? So there should be a parentheses right here.
Did you switch it?
Flip it and multiply both sides. Yep.
No, I'm saying, did you switch x to y?
Yep. The first step's always to switch the x and the y. So I distributed that 3/2 on the left side, and then on the right side, those fractions just canceled out to give you a 1y. So there's my inverse. Now, again, if you're like, I've never seen this step, some people do it in 2 parts. They multiply everything by 3, then they divide everything by 2. It's the same thing. All right, here's where it gets not super hard, a little harder. Now we're just verifying that 2 things are inverses. So it'll give you 2 functions. It'll say, are these functions inverses? To see if they're inverses, first of all, you could go through the process that we just did if you wanted. That should work. Or here's the more precise way to do it. You do a composition of functions. So you plug g into the f function. See if it simplifies to give you x. Then you do it the other way. You plug f into the g function and see if it gives you x. Oh, all these variables. If both of these work, then they are inverses. So we want to verify that f and g are inverses. So we just do the composition of functions. We're going to put the g function in for the x in the f function. Then we're going to put the f function in for the x in the g function. If they both simplify to leave you with just an x, then these 2 are inverses. So let's go ahead and test that out. Let's first do f of g of x. So I'm going to rewrite the f function, but instead of the x, I'm going to put x plus 3. So you can probably already see how this one's going to turn out. X plus 3, and then you have the extra minus 3. what would that give us? X. So it works up there. Now I'm going to do it the other way. Now I'm going to start with the f function, and I'm going to plug it in for the x in the g function. So we start with the innermost function. Remember, you're kind of working your way from the inside out. So we're going to start with that. We're going to plug it in for right here. What would we get there? X. And that's what we want, right? So, yep, these are inverses. Or, honestly, if you just showed me that they both gave you an X, that's verifying it in my mind. If it said, are they inverses, then you'd have to put a yes or no. But verify just means show me that they are. Here's the next one. Same type of problem. We're just verifying that they are inverses. Alright, so I'm going to start by plugging the g function in for the x value in the f function. So I'm going to start with 2x minus 6. I'm plugging it in to 1/2 x plus 3 for the x. Now, you'll distribute that 1/2. That'll give you 2 minus 3 plus 3. We've already sort of done this part. We know it gives us x. All right, now I got to check it the other way. So now I'm going to plug the f function into the g function. So I start with the 1/2 x plus 3. And I plug it in for the x in 2x minus 6. So I'm going to distribute the 2. Subtract 6. What do we get? Good. So I just showed that f of g is x and g of f is x. So I verified that these are inverses. Any questions? So we're kind of back to that first set of examples we looked at. Find the inverse power function. So we're just finding the inverse of this function. So I'm going to take the x, put it in the f of x spot. Take the f of x, put it in the x spot. And then I'm going to solve for the f of x. So again, I mentioned this earlier. Remember, f of x is the same thing as y. Just treat it like a y. Now, these are a little harder just because the algebra is a little harder. What would I do here? Not yet. You got to divide by that negative. So I have negative x equals f of x squared, then what? Take the square root, good. All right, let me explain that step. All they did was switch the order here. So when you take the square root of this side, that would leave you with just f of x, right? But we're not talking about f of x. That was the original function. We're talking about the inverse. So once you get to your answer, just show that that's the inverse by adding the negative 1. And then you're just taking the square root of this side.
So why did they switch it like square root of negative x equals?
Usually, this is the same thing as the y. Remember, usually you just write it in the front. Like y equals mx plus b. It's the same thing here. It's just a more difficult function. All right, here's another power function. It is written with function notation. I can sense from your anxieties a bit that function notation is not something you feel the most comfortable with. So at the next step, this step right here, change the f of x to an x and change the x to what's easier? A y. Make that step a y if you want. I'll show you with y's at the end. But if that just creeps you out solving for the function notation, change it to a y, but then at the end change it back to the inverse function notation. Okay? So how would I solve something like this? Divide by negative 27. So a lot of you will have y to the third here. How do you undo taking something to the third? Cubed root. Good. So I'm going to take the cubed root of both sides. When you take the cubed root of this, that would just give you your y. But since we're talking about the inverse, I just wrote in function notation and I added the negative one to show that this is not the original function. This is the inverse of that function. So this just went to right here, and I can show it with a little more detail in a second. Let me get the full answer up there for you, though. You can leave that the way it is. Now, a lot of you, like I said, are kind of freaking out about the function notation. So let me just show it to you if you would do y's. You would still divide by that negative 27. And then you would take the cubed root of both sides. So you get the cubed root of x over negative 27 equals y. But I want to write the y in the front, and I want to write the cubed root part in the back. You can put the negative with the x or with the 27. It doesn't really matter. Oh, that's kind of covered up for you. I'll write it up here. So when you do it with y's, you end up with the same thing, and then just change it to function notation so that I know it's the inverse. All right, so if the y's help you, go with it. If you can handle the f of x, go with it. Whatever makes it easiest for you to find the solution. Find it and run with it. Any questions? So again, if you missed that one, whether you did the y or the function notation, you can simplify it a little more because we can take the cubed root of 27, and then the cubed root of a negative number is always negative. Questions on number 7? All right, here's number 8. So this is similar to that one we looked at where there's some restrictions on our domain. That's this part right here. It's telling us that we can only plug in what type of numbers? Negative. We can only plug in negative numbers and 0. Okay, and we'll probably see why that's the case as we work through this, but just keep in mind that that's where we're at the moment. All right, how do I want to start this? Yep. So I'm going to change my f of x to an x and my x to an f of x. What do you want to do with both sides? Yeah, you want to take the fourth root. Again, what happened here is we took the fourth root and then wrote it in the inverse notation. And then you'll just have the fourth root of x. Now, whenever you take the inverse, what happens to the original domain? It becomes your... Okay, let me rephrase it this way. Your original input is now your output, right? So now this is saying the y values. Oh, that must change the sign too. I'll have to look into this one. I think they meant to say greater than 0 on this one. I'll have to double check. But that's why we didn't do the plus or minus, because they specified we only want to look at one sign. I believe this is facing the wrong way because we're only looking at the positive solutions. I will double check on this one and get you guys an answer before you leave today. But yeah, if they're restricting the inputs for your inverse, that just restricts the outputs. So we wouldn't have to look at both positive and negative, just one or the other. The way it's written now, though, I would just look at the negatives, but I'll check on this one for you. I believe this is straight out of the book. It's probably just typed wrong. But yeah, if not, if that wasn't restriction, that restriction wasn't there, we'd want to look at the plus and the minus. All right, let's look at some graphs. So you guys do have some graph paper. This says graph the f function, then use the graph to determine whether the inverse of f is a function, and then you're going to graph the inverse. So lots of stuff going on in this one problem. Now, there are a couple ways to do this when you're graphing inverses. You can graph the first one and then change the x's to y's in the equation and then graph that one. Or you can do an input-output table and switch your values. I'm going to show you it with the input-output table. So I'm going to do my x's, I'll use function notation, and my f of x's. So let's plug 0 in. What would you get when you plug 0 in? 0 times negative 2 is 0, plus 3 is 3. Good. When you plug a 1 in, you would get negative 2 plus 3, which is negative 2. And when you plug 2 in, you'd get negative 4 plus 3, which is negative 1. Good. So I'm just going to graph those ordered pairs. I have 0, 3, I have 1, 1, and I have 2, negative 1. Now, if you use M and B, you know you'd start at the y-intercept of 3, and then your slope tells you go down 2, right 1, down 2, right 1. So you'd end up in the exact same spot. I just like doing the table, and you'll see why in a second. It's going to make our inverse very easy. Oh, that's a little off. All right, so there's my original graph. Now, it asks us to determine whether the inverse would be a function. Do you guys remember how we did the vertical line test previously? If you're trying to see if the inverse is a function, you actually do the horizontal line test. So now you're kind of looking at it the other way. Are there any horizontal lines you could draw through here that would hit at more than one point? And the answer is, of course, no. So that means that our inverse will be a function. And you can actually double check when we graph the inverse. So now I'm going to make another xy table. But it's the inverse, so I'm going to use that little negative 1 notation. And now I'm just switching them. So instead of 3 being my output, 3 is now my input, and 0 is my output. The 1's flip-flop, which of course doesn't really do anything. So all I did was take all my inputs, make them outputs, all my outputs, and make them inputs. Now I can graph those 3 points. So the line you're about to see in black is the inverse graph of the red line. Now I'm going to add an additional line for you. See if you give me just a second. What's the color I haven't used? Let's use green. So I'm just going to draw in that line y equals x, that is the line that these should be symmetric across. So if I took this and folded it up across that line, do you see how the red projects on the black and the red on the black? So these are symmetric. That's what they mean when they say you just kind of reflect it across that diagonal. Yeah, it's a mirror image if you would fold it upon itself. Yep. So if you graph an inverse and it doesn't appear that they line up like that, you need to recheck what you did. Something went wrong. Any questions here? Do you want to see how to do it the other way? I can do it real quick. Okay, the other way to do this, if you don't like tables, would be to use the slope-intercept method on the red line, right? The original. You guys are, I'm assuming you're good with that. And then you would do what we did earlier. You would change the f of x to an x and the x to your f of x. And then you just solve for f of x. So you subtract 3 from both sides. And then you divide both sides by -2. So you would get -1/2 x plus 3/2. So you would start at basically 1.5 on your y-axis. And then from there you would go down 1, which would take you to 1/2, and then right 2. You should get the same line.
I think you made the one.
Okay, so I graphed it wrong. I went to the went out 3 and went over 2.
No, just because it's a fraction. Yeah, this is still your intercept. How did I get the negative? Which part?
1/2.
Because I divided 1x by -2.
Oh, okay.
So this is one way to do it if you don't like tables. I think the tables make it really easy. And the tables are always going to work. This method kind of gets tricky when you get into things like square roots and fifth roots and stuff like that. Other questions? All right, here's the next one we're going to look at. This one I'm definitely going to do with tables because, of course, this is going to introduce a cubed root. It's going to kind of be a little more difficult to graph. So I'm going to start by making a table. So I'll plug 0 in. When I plug 0 in, I get 3. When I plug 1 in, I'd get 4. When you plug 2 in, you'd get 11, right? I'll just put that so we know about it. Now this one you'll probably need more than 3 points because it's not linear. We know it's going to be a cubic, so it's that one that's kind of like an stretched out S shape. When you plug -1 in, you would get 2. And when you plug -2 in, that would be -8 plus 3, that would be -5. So let's go ahead and graph those. Okay, I can't really go up to 211. I'll put a dot up there just to show us kind of the shape of this. The -1, I go up to 2. And the -2, I'm down at -5. And then we connect it with one of those smooth curves. So that's the original. Now remember, before we graph the inverse, we're trying to determine if it's going to be a function. So this is where you'd look at it, the kind of the vertical line test, but tilted over. The horizontal line test. So is there any place, if I reflected this across the line y equals x, where it wouldn't cross the vertical line test? Meaning now it's not crossing the horizontal line test? The answer is no. it's not going to be a problem. So we can definitely graph it. It will be a function. We'll be fine. All right, so I'm going to do that same table for the inverse, except everything's going to switch spots. So now it's 3, 0, 4, 1, 11, 2, negative, oops, 2, negative 1, and negative 5, negative 2. So you should get something kind of like that. This one's kind of pretty. Now again, think of this line. It goes sort of diagonally through your coordinate plane. That is the line y equals x. And you can see that this is symmetric across that line. So if I folded these graphs upon themselves, like you probably did that in grade school, like with a paper plate, you drew like half a butterfly and then you fold it and it's full butterfly. Same thing here. It's going to line up when you fold it. Did you guys not do that? Yeah, with the paint and the butterfly. Yeah, okay. So just think back to your painting days when you were younger. Yes, when you fold them, they should perfectly line up. Any questions? All right, real quick. I am changing the directions on one of the sections for your homework. I will remind you about this tomorrow as well. But that last section, I do want to see the inverse graphed. I don't just want to know if it's going to be a function or not. I want you to actually graph it. And you guys know that's kind of an easy step once you already have your original input-output table. Let me know if you have questions, but you do have all of class period tomorrow to work on this assignment.